GeoGraphix is a fully integrated GG&E application running on a common relational database model within a robust project management shell. The mapping applications are built upon Esri technology and natively integrates with the ARC services. Links to the OpenWork database are provided by the GeoGraphix Exchange and Volant tools. Bidirectional transfer is supported by the GeoGraphix Petrel connector for complete integration with Petrel project and GeoModel. 2015.1 is the first update to the feature-rich 2015.0 version that was released at the end of last summer. In the upcoming demonstration, I will be highlighting many of these new features within the context of an integrated workflow. Coming in December, we will be releasing 2015.1, which will build upon the momentum of 2015.0 and provide greater stability, increased performance, and new key features to the software. I believe the best way to introduce the new features of 2015.0 and 2015.1 is within a workflow so that you can appreciate the tighter integration between the disciplines and the improvements in the presentation and ease of use. We'll be looking at the Barnett within the Fort Worth Basin of north central Texas. I will be doing an integrated unconventional workflow from evaluation through drilling and geosteering. In the geology workflow, I will interpret the structure of the Barnett and adjacent formations, pick the target zone based upon a petrophysical model, and model the target surface in 3D. In the geophysical workflow, I will examine the geophysical interpretation, view a semblance time slice to delineate geohazards, and create and apply a 3D velocity model that can incorporate interwell picks to refine the velocity model down the horizontal borehole. I will then integrate the geophysical interpretation into the geomodel by sourcing key surfaces in the geomodel from depth-converted seismic horizons, and then view the integrated interpretation in 3D. In the engineering workflow, I will create a multi-pad, multi-well field plan along the target surface and then create a mechanically drillable well plan for export to the drilling department. All this will be viewed in 3D environment in real time. Finally, I will geosteer the well within our new web geosteering application and update the geomodel from the geosteering interpretation in SmartStrat. Now on for the demonstration. I will begin the demonstration within Smart Section. Smart Section is our cross-section, correlation, mapping, and geomodeling environment in GeoGraphix. Behind Smart Section is a robust 3D engine called Frame Builder that I will be taking advantage of in the workflow. I've got a 3-well cross-section here in the middle of the map, showing the vertical wells from the Pennsylvanian through the Basal Atoka, Upper Barnett, Barnett maximum flooding surface, Basal Barnett, Canberra Ordovician Ellenberger carbonate. Currently, all these surfaces are being modeled independent from one another by Frame Builder. Frame Builder, again, is our topology engine running in the background. But by applying our conformance technology, in this case, based upon the Basal Atoka, the orange surface here, all of these other surfaces are going to be subordinate and therefore conform to the Basal Atoka. When I apply the conformance technology, you'll see now these surfaces are now running parallel to one another, obeying the principle of original horizontality and making a much more geologically pleasing looking cross-section. I'm going to select this well, and we'll examine this well in PRISM, our petrophysical application. You're looking at PRISM, GeoGraphix Petrophysical Analysis application. I'm running a multi-mineral model looking at 6 different phases of competent components of sandstone, limestone, and dolomite, and also the shale clay components of kaolinite, illite, and chlorite. Understanding what your clay components can be very important to how you drill and complete the well. For example, I'm analyzing for illite. Illite is often associated with montmorillonite, smectite, mixed layer clays, and could be a drilling hazard if you drill with fresh water. You can swallow those clays and plug up any porosity or permeability you may have. I have a component of kaolinite. It's a relatively innocuous clay. I'm also looking at chlorite, which is an iron-bearing clay, and could be a problem if you acidize during completion. You would liberate the silica and again plug up any porosity or permeability you may have. Now the orange up here is the top of the basal Atoka, the dark green is the upper Barnett, the light green is the Barnett maximum flooding surface, the blue down here is the basal Barnett, and at the bottom we see we have the Canberra Ordovician Ellenberger carbonate. I'm going to draw your attention between the maximum flooding surface and the basal Barnett, where we have this buildup of our competent components. Notice the average and effective porosity in here. Knowing what your effective porosity in your competent components is important because that's where most of your storage capacity is. I'm also analyzing for TOC, so we have a good TOC cut through here. And I've got these 4 tracks here where I'm cross-plotting the curves of rho B against gamma ray, phi n against gamma ray, deep resistivity against gamma ray, and shallow resistivity against gamma ray. And where you lay those curves one on top of the other in an area that you consider to be inorganic clay, like here, where those curves cross over, which I filled in with a shale area fill, is an empirical indication of organic clay. So it looks like this would be a pretty good target for doing our drilling. So let's return to our geomodel and let's change our template. Flatten on the maximum flooding surface. Now I'm running the same geomodel as I used to analyze in Prism. So there's my clay minerals geomodel and my clay minerals log template. And it looks like right through here between the maximum flooding surface and the basal Barnett, this would be our good target surface. So let's add a target surface to our geomodel. Target surface right there. Turn on our surfaces, make that the active surface, and use our picking tools to pick where we want this to be. Now I'm using our new Quick Picks mode. This is new for 2015.0, which will allow us to very quickly pick tops. Now I can now move these. Say I said, well, no, maybe it should go up there. No, maybe it should go down there. No, I think I was right the first time. You have a multi-level undo before you actually commit this to the database and to the geomodel. Once you're happy where your quick pick is made, you save that to the database in the geomodel and return to the map and turn on our target surface, and you'll notice now it's mapped over the convex hull of the extents of these 3 wells. Now if I go into the geosurface model properties and interact with Frame Builder and put the target surface in its correct stratigraphic position within the hierarchy of conformance and let it model on through, you'll see now that we're conforming to the basal Atoka, and this target surface is now filled out over a larger area. Now fortunately, I have a 3D seismic survey over the entire area. This line is the same line of section showing the same well that I analyzed in Prism. I've got a synthetic seismogram to tie my geology to the geophysics. So the M marker is up here, that strong positive reflector. The basal Atoka is this strong reflector down here, down through the upper Barnett, Barnett maximum flooding surface, basal Barnett, and the Ellenberger. Now I have mapped 3 of these surfaces in 3D. I mapped this upper M surface in time, the LS limestone marker in time, and a smooth Atoka surface in time. I'm going to use these 3 surfaces to create a 3D velocity model to better refine my conversion from time to depth. So in depth conversion, I'm going to create a velocity model, and I'm going to back interpolate the time value for each of these horizons, the M, LS, and A, and associate it with its formation depth pick that's in well base for the M, LS, and basal Atoka. In addition, I'm going to incorporate any interwell points that I may be putting in from SmartStrat when I geosteer this well. Now let's apply our velocity model. And notice when I do, these time-converted markers will snap right to their corresponding horizon. There. Now we've got a very robust velocity model to use to convert from time to depth. In addition, I did a PostAct processing using LMKR's new GeoGraphix attributes tool. This allows me to do PostAct processing on the seismic data to give me a time, frequency, or expression-based attribute. I've used a spectral decomposition and a frequency-based attribute of semblance and loaded that in as a time slice. This time slice is through the Atoka, and notice these onion-skin looking features here. These are the results of caving in from the karst topography on the top of the Ellenberger. And this caving in and syntectonic deposition was going on through Barnett up or through Atoka time. These constitute geohazards. These are conduits for water, and we want to make sure we stay away from them when we actually drill the well. Now let's return again to our geomodel and go back to our original template. And let's apply our original vertical wells initial template. Now I'm going to combine my geophysical interpretation with my geological interpretation by sourcing this surface that I made called the Atoka from SeisVision, not from the data points in Wellbase, not from my ISOMAP grid, which I could, but from the actual SeisVision interpretation, this B-shell interpretation for the A horizon. Now in addition, I'm going to take the Atoka from SeisVision and make it be the controlling conformance surface so that the basal Atoka and all subsequent surfaces will conform to the seismic surface. However, these other surfaces will honor their well picks. I'm going to apply that. And notice now we have a much more detailed interwell conformance from the Atoka from SeisVision down through the basal Atoka, through the basal Barnett, Barnett maximum flooding surface, basal Barnett, and Ellenberger. And when I turn on the depth converted seismic backdrop, you'll see the strong positive event, which was indicated by the synthetic as the Atoka, is spot on our geomodel. Returning to our map, you'll see we have a much more detailed target surface that we can use now for doing our field plan. But before we do that, let's take a look at what we've done right now in our 3D environment. I've drawn a selection polygon here over this area. I'm going to take all of the 3D objects within the bounds of this rectangle and load them into our 3D environment. It'll take the surfaces, the wells, and the cross section as a fence diagram. So let's take a look at that in 3D. And here we are in our 3D environment. Now I can use the keyboard to navigate, or I really do prefer using an Xbox controller because we really are in a 3D environment, and this application is built with Xbox gaming technology, so I'm going to use an Xbox gaming controller. I'm showing the fence diagram with the lithology based upon the lithology that was in the Strat Column Manager. These are the surfaces that were also generated by the Frame Builder geomodel. For now, let's just go ahead and turn off the surfaces and focus in on the cross section. Currently, I'm showing the lithologies, like I say, that were brought in from the Strat Column Manager. But I can also load in any kind of petrophysical attribute. In this case, I'm going to be pulling it from a certain curve set. And I'm going to pull it in the gamma ray, and then change from the lithology to color fill. And now I am interpolating the gamma ray values along the face of the fence diagram. New to this version, I've got a histogram control that I can limit the area of the color control to bring out or highlight the attributes I'm looking for. So in this case, the green up here is showing the more shaly parts of the Barnett, and the more tan color or the more non-shale components. Zoom in a little bit closer. Click on the surface to select the surface of the fence diagram. Right click and I can display a depth converted seismic section behind it. By adjusting the opacity, I can co-blend the petrophysical attributes against the geophysical attributes. And if I had an attribute volume that was showing some other attribute, I can then co-blend them together to see if there's any kind of correlation between the petrophysical or geophysical attributes. In addition to this, I can also click on the Seismic and show a slice of the semblance volume. And let's look at that from above. Scroll down, let's change the palette. Semblance is really better looked at in a grayscale. Now let's just animate down through from the Atoka down through the Barnett, and you can see these onion skin looking features. Those are the collapsed features from the Ellenberger constituting the geohazards. So let's remove the Seismic and go back to our zoom to fit and come up and look at the cross section again and remove the Seismic. And return back to Smart Section. From here we're going to take this surface, which is our target surface in ISOMAP, and go over to Geo Atlas. In Geo Atlas I'm showing the target surface. I'm showing a lease boundary with a 330-foot buffer. This buffer is a boundary that I do not want to drill beyond because of legal reasons. I'm also showing some drilling windows presented to us from the drilling department. And over here I've got several other ISOMAP surfaces, the M surface, the LS surface, the basal Atoka, the upper Barnett, and the Ellenberger that I also made from the GeoModel and Frame Builder and converting them to ISOMAP surfaces. But I'm just showing the target surface right now. Now let's zoom into our drilling windows. This is where we're going to be doing our field plan. So I'm going to launch the field planner from the Pro toolbar in Geo Atlas. I'm going to make a new field plan. Let's just call it Field Plan A. Now I've got some other pads out here, but I'm going to use the Auto Pad feature to go ahead out here and click where I want the first slots to be. It captures the XY of the slots. I want 3 wells for those 3 well windows in each one of those. I'm also going to back interpolate from a digital elevation model the elevation of the pads. The azimuth is 180 degrees, and from the drilling department they give me the well spacing of 665 feet, step out of 150 feet, kickoff depth of 3,500 feet, heel to toe 10,000 feet with a minimum length of 1,000. My target layer is the Barnett target surface, and my lease layer buffer is this Anadarko Leases 2. Let's update the layer. And I'll turn off the target surface to better let you see these Wellbore diagrams. Notice that they are stopping at the edge of the lease buffer, but in this case this one is extending beyond the drilling window, but I can simply click on it to select it and move it back manually. Now that we have the field plan built, it's time to go ahead and build a mechanically drillable well plan. So I'm going to save the map, and I'm going to launch LMKR Well Planner on one of our new GeoVerse applications. And let's look at this area in 3D also. I've got that same polygon on my GGX gusher layer. I'll highlight it, view that in 3D. I'm going to add that to the currently active scene. And now it will load in all of the ISOMAP layers that were shown in left-hand window here. These ISOMAP layers are being automatically loaded into the scene. And for now I'm going to turn off all of the surfaces except for our target surface. And let's zoom into the area of the target surface in our 3 well plan. And let's move down a little bit and zoom in. Notice that the field plan is landing spot on our target surface for the heel and the toe, but now we have Well Planner, which will allow us to actually build a mechanically drillable well plan. So here's the field plan, and here's our field plan number 1 well slot, which is showing right here. When I click on it, it immediately loads it into Well Planner and starts to build us a mechanically drillable well plan based upon whatever dogleg severity for the approach and the lateral we put in here. Now let's zoom into the vertical section here. Now notice we landed here on the Barnett target surface, and the toe and the heel are on the target surface, but notice it does not follow the structure of that target surface. Now we can manually put in guide points, but I'm going to let the computer do it by adding 5 guide points. You can see that it snaps right to that surface, shows the same guide points on the 3D surface. If I move any one of those guide surfaces, it immediately updates in 3D. And if I move it too far and get it to be in red, it will show that I've exceeded my guidelines of my dogleg severity and is not mechanically drillable. So let's return it back here. Something like that. That looks good. Look at the 3D view. This is sort of a QC view of our well. Go to the Survey tab, and this is the survey of our targets, and I can export this to Excel. So here are our targets, and then you would give this to the drilling department, and they would put it into their computer models to go ahead and build their own plan. Next, let's look at the Geoprognosis tab. This will generate a geoprognosis for you that you can also export to a Excel spreadsheet. And it will give you a prognosis of where you expect to penetrate the surfaces, the M surface, the LS surface, the basal Atoka, the upper Barnett, and then the Barnett target surface is encountered several times as it porpoises down the horizontal reach of the well. Now that we've planned the field plan and we have designed a mechanically drillable well, let's go ahead and drill this well and geosteer it. I'm going to be doing the geosteering in LMKR's new GeoGraphix web steering application. This is a browser-based application that is very light, very easy to load, and very fast. It can run either on your network, across a VPN, or it's actually self-hosted and can be completely off the network. In the Setup tab, you initially make your connection. In this case, I'm using my computer as my server. In your case, it'd probably be your project server, to make the connection to your project home, your project, your AOI, and your datum and map coordinates. We also support WITSML for 3 providers, Digidrill, Passon, and Petrolink. Once the connection is made, you go to the dashboard. We're going to geosteer this well, and I can type in the first few characters of the UWI and search for it in GeoGraphix, but in this case I've already got it set up. And then the surveys can be easily loaded in from an Excel spreadsheet. So for example, I can drop this one in, parse out the columns, and it will build your survey plan. Now I've already started drilling this well, so I've already got one loaded in. Likewise with the LWD, this is the logging while drilling, I can drag in an LAS file and again choose which curves, primary and secondary, you can put multiple curves in here, I want to use for my LWD. In this case I've already got the LWD loaded. For the type log, I can do a search radius around this well if I'm connected to the project, or likewise I can drag in an LAS file, parse out where the curve is, and load it in. I've set my target formation as the upper Barnett because we're going to be drilling into that. For the grids, once I'm on the network, I'm on my VPN, I can select any of the isomap grids that I built for my geomodel and use them as a backdrop on the vertical section. Now I'm ready to geosteer this well. Now it starts out with the initial point of the segment, or the dip segment or strat segment, whatever you want to call this, at the intersection of the active surface with the wellbore, and extends out some distance. Now I can adjust the distance out in which I want to do the geosteering by simply clicking on the endpoint, and it adjusts the segment that I'm going to be looking at. Now I'm going to be looking at my initial segment in here, so let's zoom in a little tighter and take the endpoint and adjust it until it matches our type log. Maybe a little higher, something about like that. That looks good. Click the new button, that saves it and creates a new segment, and we'll drag that to a new point, something there. And again, we'll adjust this until it matches our type log. Create a new segment, and we'll drag it to this little notch right here. Pull it down until it matches. Create a new segment. Let's drag this down a little bit so we can see it a little better. That's good. Maybe it's about there. Stretch it till it fits my type log. Looks pretty good. I'll do a couple more. And finish it up. Do that fine little adjustment right there. Now this has created a number of segments giving me my dip and dip azimuth and other information that's stored right here in the browser database itself. Now when the next set of drilling information comes in, either from WITSML, which would be a constant feed, or from the LAS of the LWD and the Excel of the survey, you simply drop them in just like I showed you and continue on. Now the beauty of this is it's very lightweight, very easy to use, very fast, but it integrates directly back into your project and your smart section geomodel. So once you're back on your firewall or on a VPN, you can then export this into your smart section interpretation. This is the smart section interpretation we were using. And then returning to smart section, it will automatically load it into your list of cross sections in your interpretation. So there is the line of section right there. So let's go ahead and open it and turn on SmartStrat. SmartStrat is Smart Sections geosteering application, so you can actually do your geosteering right directly within the geomodel. It knows what the type log was that you used from web steering, and it's also showing the geomodel here. The orange is the basal Atoka through the upper Barnett maximum flooding surface, basal Barnett, and the Ellenberger. Now this magenta line right here, that is your active surface or your model surface for the active surface, which is the upper Barnett. And notice that the interpretation that was done in the web steering that's shown here now in SmartStrat does not match. So we now need to tie our interpretation of the geosteered well into the geomodel. And to help us do that, I'm going to hang the type logs that we used at each of the dip segments right on the cross section. Let's close this for clarity. Zoom in. Go to our Surfaces tab. Highlight the basal Atoka. Now according to our type log here, the basal Atoka should be up here. This is what the geomodel is currently showing. So I'm going to use my picking tools, and again I'm going to use quick picks to go ahead and pick the basal Atoka where we think it should be. and also the upper barnet. The upper barnet looks like it should be right there. Of course, that's our active surface. And then go ahead and commit them to the database and the geomodel. And now, because of the conformance, everything is modeling through directly. Now you can come in here and do any kind of fine-tuning you want to, but basically we've now tied our geosteering interpretation to our geomodel. And when I turn on my seismic backdrop, you'll notice that the basal Atoka should be following right like it does here, right with that strong positive reflector. Remember in SeisVision, when I tied the synthetic to the geology and the geophysics, it showed that the basal Atoka should be a strong reflector. The reason it's not is because I don't have the information to update my velocity model. But now I can incorporate my interwell points. And just to remind you, back here in our velocity model, I'm going to be incorporating basal Atoka interwell points to refine the velocity model. So let's go ahead and update the velocity model. We'll take those depth points, combine them with the back interpolated time value on that surface, and update my velocity model. So now I've got the most up-to-date geomodel and up-to-date velocity model possible. So if I were to then decide to plan a well, say in this area, it will be planned into the most up-to-date geomodel possible. GeoGraphix 2015 supports enhanced workflows for both conventional and unconventional plays. It features tighter integration between the disciplines of geology, geophysics, petrophysics, and engineering to provide you with unprecedented value in your GG&E investment. 2015.1 update scheduled for release this December will be available at that time for download from our web support portal. You can replay this webinar and also many more by going to the GeoGraphix support portal. You can also up there look at our training schedule for maximizing your investment in GeoGraphix. Or you can request a quote by emailing products@lmkr.com and contact your regional sales manager. Thanks for attending.